Mr. K.P. Soundara Rajan, Director and General Manager of Gleason, India. And today he will be sharing his knowledge on a very important topic, that is gear tooth surface under EHL lubricants and friction. So I would like to ask Mr. Soundara Rajan to take his seat and we will start his presentation just right away.
Thank you very much. My presentation is not complicated, simple one, but I try to explain some basics, whether it is for the industry or practicing engineers or fresh. I just thought I should share something like that. So I just couple of slides I put. So basic things, let me explain and then see if you have any questions on it. This is gear tooth flank surface under EHL, gear tooth flank surface under EHL lubrication and friction. Let me explain some general thing basically. Gear tooth flanks taking a drive between the driver and driven parts. Of course, on involute tooth, I don't go for cycloidal or anything. And how the loads are transmitted. And in the process, what happens is, it's not only the load, there is something known as friction because there is a metallic contact. And to avoid friction, and to avoid metallic contact, we have lubricant coming into the picture. So when we have lubricant, let us concentrate on mineral oil with or without extreme pressure additives. And what happens to the tooth flanks or the combination of driving and driven tooth flanks in presence of oil, mineral oil, which has got some physical and chemical properties, as to how it transmits the load and what happens in that. There's some physics behind that. This is something which is basically, we say, Strebeck curve. Many of you would know this. It's a fundamental combination of certain properties in lubricated tooth flanks or lubrication, where H is N omega by P. One is the viscosity, the other one is the angular rotational speed and angular velocity, and P is the pressure. So we are trying to put the friction, as a parameter of the y-axis with respect to what we know as Hersey number. So we have three things. One is boundary lubrication, mixed lubrication, and elasto-hydrodynamic lubrication. You can see as we move from boundary lubrication, where the contacts are between metal to metal, and then over the mixed lubrication along the length of line of action, certain portion have metallic contact, certain portion are separated by thin film. So thin film lubricant. And third one is the contact is separated, totally the load is taken by the film. Automatically, under normal circumstances, the friction will come down, so the coefficient of friction is less. This is something the same thing which is picturized with respect to something known as slide to roll ratio and friction. Slide roll ratio is one in the pair of gears between the sliding and rolling velocity of the meshing pairs. If the rotation movement of a driving gear to driven is divided into two components, one is rolling, other is sliding. At any given time you can geometrically find it. You draw the line of basic tangent between the two base circles and draw the involute curve. Any point you see and connect it to that, draw normals to the respective tangents. You get a component of velocity. One is rolling, other is sliding. Both have different purposes in movement. Some is good, some is not good. So naturally, rolling velocity is helping to put the oil inside the tooth flank when the two gears are running. So we call it as entrainment velocity. In future slides I will keep on saying entrainment velocity. Remember, that is rolling velocity. The sliding velocity will be something which will create heat because due to friction. So you will have a negative friction, or we say changing friction directions. So that phenomenon comes out of sliding. Both have a different effect in terms of friction also. So we have the relationship between slide roll ratio to friction as a base. So up to certain portion of slide roll ratio, if you increase from 0 at the origin, it will go initially linear. and thereafter it goes non-linear. That is where the interest lies, because the behavior will be non-Newtonian there. And thereafter there will be a plateau, and then it will drop, friction will come down because the thermal effect will start coming. That is where, like Mahendran said, when the high-speed gears go, friction, he was talking about scuffing and all those things. We will deal in the scuffing in those circumstances. This is, I can skip it also. You will know there are different kinds of thing which is known as iso-viscous rigid, piezo-viscous rigid, iso-viscous elastic, piezo-viscous elastic and all. This you can always, if you want, I don't want to read it, between the two things, when the load is applied on the tooth flank, in presence of lubricant, it is shared, the load is shared by the lubricant and as well as the driven material member. So in that what happens is, when the load or the pressure increases on the lubricant film, it tries to resist it as much as possible, because oil will not just allow to take the load as it is. Up to a certain level it will be behaving like a Newtonian level, whereafter it starts deteriorating as the shear ability of the oil changes with respect to applied load, and then it becomes non-linear. So obviously the divisions of piezoelectric, piezoelectric elastic and piezo-viscous rigid and all these things are defining at which point the lubricant is allowing to change its viscosity, at which point the force acting on the member of the tooth driven flank that influences, and in which circumstance both are changing. They are the four different things. This figure has not come correctly, but you can see it is a combination of two gears in mesh or moving. So I just try to show how the oil gets into the tooth flank on an involute, as well as it can go into the tooth flank in the y direction. This is something on the elasto-hydrodynamic situation. You can see the driving and driven situations, and the oil is going inside. The HC becomes the central film thickness, and in the process, when the oil goes inside, there are two things which are known as the flow of oil, like I said, entrainment velocity throws the oil inside, and the load is being applied, and consequently the oil film undergoes the pressure on it. So momentarily it stands, and then it tries to increase its viscosity out of pressure viscosity coefficient. And thereafter, when the resistance comes inside the film, it resists the oil flow further. Therefore, the surface flow has to overcome that, because there will be a creation of pressure inside. In subsequent sketch, I will show you how the pressure changes, but this is what is happening inside the contact. This, you need not read it, but I only said there is a pressure rise inside the film, and this pressure rise causes resistance to further inflow by entrainment speed, and consequently there will be change in increase in pressure in the tooth flank, depending on the type of load, depending on the lubricant physical property. That pressure can change its position with respect to pitch point towards the dedendum side, or what we call it as exit of velocity. This is basically the mean U1 plus U2 is the rolling velocity of the driver, rolling velocity of the driven, which becomes mean entrainment velocity. H minimum is the film thickness. This is according to famous Dawson-Higginson equation. You will have all the properties like the radius of curvature, and then viscosity parameter, Young's modulus, pressure viscosity coefficient, density, and all those things. This is the film thickness which is normally used in design in calculating the required film thickness out of standard, where we say pitting standard, micro pitting avoiding standards, which calls for two methods of calculations. So it is quite often used. So when the EHD is taking place between the two meshing teeth under load, when the pressure increases, then it causes certain viscoelastic traction as the shear stress occurring on on the oil film is exceeded by the applied load. So the applied load starts working against the film. Naturally, there is a point at which it shears, and thereafter the behavior of shear stress to shear strain becomes non-linear, which they say non-Newtonian behavior. So in that, there is a parameter what is called as Deborah number. The Deborah number says the viscosity in terms of pressure and temperature, because at that time the temperature will start rising into the third level where I said thermo effect in the previous slide. So it is also a function of rolling velocity or the entrainment speed divided by Hertzian pressure on the invalid tooth flank, which is called semi-bandwidth of that. G becomes a shear modulus of the oil. Now the definition of shear modulus is taken in terms of these parameters, sir. You need not worry about that. So because of this Deborah number, it is interesting in the tribology for the simple reason along the tooth flank in the meshing cycle from 0 to 1, you can see how the Deborah number keeps changing with respect to the length of line of contact. So the thick one is what is known as LLTCA, which means TCA is tooth contact analysis, LLTCA is lubricated loaded tooth contact analysis. There is a difference between the two. This is the three-dimensional thing where slide roll ratio versus entrainment speed with the friction coefficient, how it changes in different zones. In the linear zone, how it is, and in the non-linear zone, how is it, and the mixed zone, and how it changes to thermal value. What I said, basically TCA and LTCA, these are the inputs for that. Conventional TCA analysis will have gear material and theoretical tooth profile and gear rotational speed, whereas rest of the things will take into lubricant property also, as well as measured involutes as value put inside. This is the value which is used as a friction coefficient, and it is fed into the FEA resolver, and from there the friction coefficient is calculated by Evans and Johnson, which is used in the film thickness calculations. So we see how the meshing cycle with different entrainment speed can give the various values under lubricated loaded tooth contact analysis as well as conventional tooth contact analysis, more precisely with LLTCA, that is what is preferred. I skip this because these are basic definition of how Reynolds number is used in defining the film thickness, and you have two directions of motion lubricant oil in the X direction and perpendicular direction in Y, which will cause leakage. If you assume that leakage is not there and in X direction it flows, that will be equivalent on the right hand side is the rolling velocity or the entrainment speed with respect to X, with respect to Y, and how the film thickness can change with respect to time. Because that fact is added, term is added because continuously if you do with the EHD, it gets into mixed lubrication because of heat developed due to friction as a passage of time. This is a simplified one. We removed Y from here, and below one is the elastic shape of the film, where we take the film thickness as the shape of the two meshing flanks as giving a way for the oil to form a film thickness, and second is the surface roughness on the driving flank and driven flank put together. They are algebraically added together. This is same thing, Fourier function and Couette function for the transient flow. This is what could be interesting when the two tooth flanks are running together, and if they have surface finish on the surface roughness on the driving and driven flank, they move with certain speed inside. At the same time, the oil is getting inside due to the entrainment speed. So depending on the roughness amplitude, the speed with which the oil is getting inside will be different from the amplitude of surface roughness getting inside. So there is a change in these two which causes fluctuation in film thickness. It was found sometime by one Lubrecht, which I mentioned in the morning. He found that when the tooth flank is entering into mesh under lubricated film, the contact pressure changes the amplitude slightly, and therefore there is a temporarily changed dynamic for amplitude change into contact compared to what is originally as a surface roughness amplitude outside. That ratio is AD by AI. It is basically a quadratic equation, and there has got a lot of material properties, speed properties and that. Today it is possible to make some software using this approach, how to compare the film thickness fluctuation with respect to surface roughness and how we can use it to define a required surface roughness to see what we can do in EV gear surface quality. This is still under research, but it's going to give some way after some time. Same thing which I put in the form of a quadratic equation. This is typically lambda ratio. If you have the minimum surface roughness as well as film thickness and surface roughness of the pinion and the gear wheel together is an RMS value, that gives you a quantity which is called lambda ratio, which is nothing but the ratio of film thickness to roughness ratio. Many times we found by practice, when the value of this particular parameter is less than unity, it is good. But where it is also unfavorable, sometimes the gear still works without any reason for knowing why it is still running, although it should have been better. This is where the previous equations I showed you, the change in amplitude automatically caused, which is different. Consequently, even a little bit change in surface roughness undergoes a change under load, and that could be useful. That's the reason why I put this the equation together. When the speed increases from low speed gear to high speed gears, beyond say 20 meters per second, 30 meters per second and all, you come into a domain of high speed gears, which is coming in aerospace, turbine quality class of gearing, ground gear. So there it is necessary to know the friction loss, for which you must know how to find the friction coefficient. So this was found by Japanese researchers in Mitsubishi some 15 years ago, which was taken as an input value in some of the ISO calculations today. This takes the basic gear geometry, pitch radius, length of line of action of the driving pinion, length of line of action of the driven pinion, and from there taking the pressure angle, we take that, and then they take the load also and put in the friction coefficient there. So here the value of the friction between in estimating the friction loss in watts of power, if the input power transmitted power is 35, 40 or 50 megawatt, the amount of power loss will be pretty high. So there is a lot of effort to save that kind of energy. So it is necessary to know the friction loss and determining the friction coefficient. So there is a parameter known as D parameter. So if the value of the film thickness by the friction coefficient, what I told you as a lambda ratio, for a moment think of the reciprocal of that. Film thickness by surface roughness, change it, you decide the surface roughness and put the required designed film thickness of a particular specification of the oil, then you can find out what happens to this D. So this quantity D is less than 1, friction coefficient is taken in design as 0.01. If that value is found on a chosen oil with a chosen film thickness, if that value is between 1 and 10, friction coefficient is taken accordingly. If the value is more than 10, friction coefficient is taken accordingly. This is useful in used as an algorithm in calculating power loss in high-speed gears today. So when the losses come other than friction, another one becomes windage loss, where the rotational speeds are high. So oil or air oil volume mixture also is thrown at a high speed, and therefore some power is consumed in moving that combination also. So that becomes a windage loss. So usually for windage loss, we take a critical value of a Reynolds number of 3 into 10 to the power 5 as a critical value in design. So if you have that value less than that value, then the loss of value alpha t becomes a Nusselt number times the other parameter, that is heat conductivity, angular velocity by density, that remaining the same on the other one. If it is more than 3 into 10 to the power 5, it becomes a higher windage loss. It is also found by experiments by Japanese, and that had a equation like this. You have 100 meters per second as a velocity. The measured loss was 3.3 kilowatts, and the below equation is the windage loss. It was measured as 3.1. At 125 meters per second velocity, you can see 8 and 8, 6.1. 150 is 11 and 10.5. These have been found useful, and I have shared it last month to ISO in the United States. There is a committee working on it, and they will also look at it as to how the thing will be taken into consideration for calculation. who has members from UK, Germany, France, Switzerland and US. So we will study this and see how we can try to use this parameter in finding the friction parameter and use it in calculation of this for high-speed gears, especially more than 80 meters per second. This is a conventional film thickness equation, so minimum and the other one, this also known value. And in those kind of high-speed gears, we don't worry about film thickness, as I said so far, on mixed lubrication and this. It is only for low speeds. When the speed is high, when the temperature goes up, then we have to find out the failure of the gear by means of scoring resistance or scuffing only. Because like Mahindran said, at that time there will be a temporary welding of the tooth flank due to temperature. So we have to see how to avoid that only by increasing the flash temperature of the oil. So we have to see how should be the flash temperature oil used in design, and in those high-speed gears more than 80 meters per second. The conventional value practiced in design is the TB limit value is 140 degrees centigrade. This value is a parameter, as a target, as a nominal value, and then this can be changed only if you have to change the tooth flank surface roughness. You have to grind the gear to 0.5 mu RA or 0.6 mu RA. 140 will change. The targeted value kept by Swiss people for this is 0.35 mu RA. And second thing is, if you happen to change the viscosity, that also will consequently change this TB limit. That standard one is at 4 degrees England at 50 degrees centigrade, which is accepted value in Switzerland today. We are trying to modify this, what happens with the higher velocity in the new standards. So there is a parameter known as A, which is shown here, because in the driving and driven teeth, the sliding ratio, sliding velocity is high at the tip. So naturally the temperature also will be more at the tip. So therefore, pinion tooth tip and gear tooth tip, we calculate the flash temperature in two different values, keeping common factor of A with the other thing called F1 and F2, which is multiplied with 140 degrees centigrade. So that A value is geometrically taken as the load transmitted by the pinion, tangential load per unit length of face width. E alpha is the contact ratio, alpha TW is the transverse contact pressure angle, V is the pitch line velocity, and A is the center distance, and again is a transverse pressure angle. This quantity is fixed and included in the standard now. From this we go to the allowable flash temperature. So for K1 we calculate for the pinion, K2 will calculate for the gear, for gears operating more than 80 meters per second. And then we use K value with U is the gear ratio. Then we take K1 and K2, multiply this to get the allowable flash temperature, which will be fixed at the design value, and corresponding oil only will be used and nothing else. This is once you do this calculations and run it, in order to find the sustainable lifetime, we do not have this S-curve and all those things. This is working on the basis of Palmgren and Lundberg, who developed this equation after the Second World War, which is still used in many countries in calculating the Weibull analysis on this. So that says the survivability of such a gear when you use is proportional to the stress level to the power of C, and N is the number of stress cycles, E is the Weibull slope, S is the maximum shear stress happening at the substrate and at which depth it is there, that is Z. H is the film thickness. So lubricant film thickness at LLTCA has the influence up to that level where the gear has to operate under extreme conditions to have its survivability against viable statistical methods. So based on this, we now find in 2022, 1 year ago, I developed new method to see how the temperature of the tooth body, the pinion body, raises its temperature by the velocity in the form of a parabolic equation. This is being examined now, and this basic equation is given there, 0.0021 x square minus 0.1188 x plus 77.8 will be considered by the ISO committee. They will come up with ratifying this, put it to ballot voting, and then some result is expected in 2024. This is the specification of the pinion wheel which I have been talking about as a driver and driven, which is number of T2083, 6 module, 20 degree pressure angle, helix angle is 15 degrees. You can see the maximum pitch line velocity is 220 meters per second. 220 meters per second, transmitting certain megawatts of power. That's why the temperature is important. This is the analysis of similar drive of those speed measured temperature at different locations shown as 1 and 2, 1, 2, 3 and 4 at A, B and this on different left and right tooth flanks, as well as the bearing of the shafts and along the helix. And the curve, this is also you can see what I showed you in the new equation. This was found in 2001, but the fundamental is same, but they only change the value on that, but this is also parabolic. So you can see in this how the pitch line velocity of this rises to particular temperature when different styles are shown. This is on the pinion, this is on the gear, and at which point and all those. So this is something which is considered together in the new standard. That is the thing. That's all. If you have any question, and then go through that. Subsequently, you have anything, you can send an email also. No, here it is without additive. But if you have additive, then there is some the pressure flow inside will change if you have a polymer based EP additive. Something like polyalkyl, methacrylate and all will have a different molecular weight that will change the viscosity inside. And also has short stretch and long stretched polymers are there. They have a different behavior. So it has to undergo a test called shear stability test. And the shear stability index has to be calculated. That has to be factored inside.
Thank you so much, Mr. Soundara Rajan. It was an intensely technical session and I hope you all would have enjoyed it. Did you enjoy or not? I just want to hear from you all. Just a yes or no?
Yes.
Yeah? Okay, great. Great.